Hi everyone. Uh, I'm Sonmuk, and I'm going to introduce this paper called Universal Learning of Nonlinear Dynamics. So let's get into right now. Uh, we are going to talk about prediction. Given observations from Y1 to YT generated by autonomous nonlinear dynamics, which is defined to be like xt plus 1 equals f of xt. And our observation is yt equals h of xt, where f and g are deterministic and unknown. Or we can also consider linear dynamical system, xt plus 1 equals a times xt plus b times ut plus wt. And our observation is linear impartial observation, yt equals c times xt. And in prediction, the objective is to forecast the next observation, y hat t plus 1. And I want to note that the state xt is hidden, which is that means we don't know the state xt, and we only know our observations yt. And it may be high dimensional. So for prediction, there are some prior approaches. One thing is model-based approaches. Model-based approaches try to explicitly learn or approximate the true dynamics F or its linearization if it is not linear. For example, if we have a linear F, then we do system identification. That means we we learn parameters A, B, C using regression. And if we have nonlinear F, then we use Kuhlmann operator. That means if we will lift our dynamics into high dimensional space, and we can find some equivalent linear dynamical system to the nonlinear F. And we do the same, but some like techniques. We use some techniques for linear F case. We also can use black box approaches. We can use models such as transformers, Mamba, or Hyena that learn mappings from past to future observations directly. And this approach is highly expressive and often achieves state-of-the-art performance. On the other hand, they lack interpretability and provable guarantees. In this paper, we want to approach this problem in another way, which is called improper learning. So we have the same setting, xt plus 1 equals f of xt, and our observation is yt equals h of xt. And the main key is for prediction, it is not necessary to recover true f and h, which has the same concept as this black box approach. However, in this improper learning, we want to also have provable guarantees. And in order to have in order to predict well, we use a different function class. And we consider learning to be a competition against the comparator model pi in some class pi. So what do we mean by comparator? So comparator model pi, or its class, is a class of ideal predictors, but not necessarily the true model class. So we want to find some ideal predictors which predicts well. And we ensure our predictor in some class A need not to be equal to a class pi. And we want to ensure our predictor performs as well as the best predictor pi. So we are not following to like recover true f and h. We want to mimic the behavior of our comparator model pi. And our performance. So the performance goal is formally written in this way. We want to have sublinear regret, RT, relative to the best pi. I want to introduce some annotations. The R is the complex disk of radius R. And well, I want to introduce spectral condition number. So for a square matrix A, which is complex diagonalizable, let kappa diag A defined to be a condition number of H, where A is equal to H times D times H inverse. So that is our the diagonalization of A. And H is the matrix whose columns are eigenvectors of A, or complex eigenvectors. And we define kappa diag of A to be infinite if A is not diagonalizable. Let me introduce some assumptions. For a linear dynamical system with ABC and with the system starting from x naught and arbitrary noise, we assume that A is diagonalizable with all eigenvalues have magnitude less than 1 and spectral condition number to be equal to 1. We assume that the system is bounded, meaning that B and C, the matrices B and C, are bounded in Frobenius norm, and X naught is also bounded, the initial point. We also assume that all inputs, outputs, and noises are bounded, and the system is observable. For a nonlinear case, all state signals are bounded. We assume that all state signals are bounded by some radius r, and we assume that functions f and h are one Lipschitz. And we also assume that some discretized linear lifting is an observable linear dynamical system, and we will define what the discretized linear lifting is later. Now we'll look at what we do. We do observation spectral filtering with regression. And they are the inputs. These are the inputs. Horizon T, the number of filters H. We use some spectral filters, which are essentially eigenvectors of some matrix, and we choose top H eigenvectors. And the number of autoregressive components, which is typical autoregressive components, we use M previous history length, and step size eta T, which will be the step size for gradient step. We also need a convex constraint set K, which will be the constraint for a parameter that we learn depending on the dynamics. And we also input prediction bound R, where R is the bound that bounds our observation YT. Okay, so let's go into the algorithm. First, we compute the top H eigenpairs, sigma j and Vj of some matrix C, where their entries are defined in this way. And when we initialize the parameters j, m, p, and n, and these are the learnable parameters that we want to learn, and we denote theta t for simplicity. So we learned we run a for loop for t. For each t, we have an observation y hat t, and y hat t is equal to some weighted sum of inputs and another weighted sum of previous history, which will be related to our spectral filtering. And the third term is also another weighted sum for our previous history. And the fourth term is a spectral filtering for our previous observations. And after we predict our y hat, we project y hat to the ball of radius r. And we compute the loss LT after we observe the data from the dynamics. And we compute the loss and we update the parameters by using gradient descent. And now we want to discuss why we do this. For the first fact, there is a class of maybe possibly high dimensional linear systems that provide the best possible observable linear representation of the true dynamics. So I want to split into two parts for linear dynamics and nonlinear dynamics. And fact 1.1 means that it says that it has a desirable this like linear system has a desirable transition matrix and generates the same trajectories for linear dynamics. And for this, and we're saying that there is a class of linear systems which approximate nonlinear systems arbitrarily well over a long horizon. And lastly, the second fact is that for both linear and nonlinear dynamics, under some regularities, for h, the number of filters, if the number of filters h is proportional to the square of log t, then running algorithm 1 produces y hat to y hat, where the regret where the loss is bounded by t, a square root of t. And we'll talk about these facts later. First, I want to talk about spectral filtering first. So observation spectral filtering, well, there are previous works on spectral filtering, and in this paper, they talk about observation spectral filtering. And I'm going to just talk about what observation spectral filtering is. And the goal of spectral filtering is to predict future observations from past data without reconstructing hidden states. The core ideas are as follows. First, they apply a set of filters where the filters are eigenvectors of a Hankel matrix. So in the bottom, this Hankel matrix is T minus 1 by T minus 1 matrix, where each entry is defined as 2 over I plus j cubed minus I plus j. And this T is the horizon length. So that means this Hankel matrix does not depend on our dynamics. It is independently defined, and the size of the Hankel matrix does not depend on the dimension of hidden states. And there are two facts. There are two facts. The first fact is that a positive semi-definite Hankel matrix has eigenvalues that decay exponentially. So when we apply a set of filters, for example, top H filters, since eigenvalues decay exponentially, we're saying that it is enough to just choose top H filters, top H eigenvectors of Hankel matrix. Also, this spectral filtering was introduced in previous works, and in the previous work, it says that if they in the previous work, they only considered it's like symmetric transition matrix A. For symmetric transition matrix A, it is easy to deal with because they only have real eigenvalues, and their eigenvectors are orthogonal to each other. But if for general like diagonalizable matrix, their eigenvalues could be complex, not real. So it is hard to deal with. And the key point of this one of the key points of this paper is that they also deal with some non-real eigenvalues as well. And another core idea of spectral filtering is that they capture spectral components of the dynamics using the filters. So that makes sense. And then it uses regression to combine filter features to predict next observation. So this inner product part is spectral filtering part. So it filters the phi I. The eigenvector filters previous inputs and previous outputs, and maybe scaled by their eigenvalues, and they are combined using regression. So these matrices J, M, P, and N, they are the weights that combines all the filter features to predict next observation. Now let's go back to our facts. So fact 1.1 was that some linear we can find some linear dynamical system that has a desirable transition matrix and generates the same trajectories for linear dynamics. We call the system Leuenberger observer framework. So given a linear dynamical system with parameters a, b, c, and initial point x naught, we can choose a gain so that x was so that uh to we can choose a gain to make another linear dynamical system. We define we define the system as follows: x tilde t plus 1 equals a times x tilde t plus b times ut plus l times y t minus y tilde t. And our partial observation will be y tilde t equals c times x tilde t, and our initial point will be the same as the original system. And the point of the Limburger observer framework is that it generates the same trajectories as xt plus 1 equals axt plus but and yt equals cxt as the noiseless case of the given linear dynamic system. We can show that by using the state error. If we define the state error psi t to be xt minus x tilde t, then since we started with the same initial point, psi naught will be 0, and psi tilde t plus psi t plus 1 will be obtained as a minus lc times psi t plus wt. And if for the noiseless case, we can show that since psi 0 is 0, then all the psi's will be 0. And one fact from control theory is that if A comma C is observable, then we can choose L to place the eigenvalues of A minus LC as desired. Then how can we find such L, the gain L? Leuenberger program. So we can find L using Leuenberger program. So Leuenberger program is an optimization problem. And so for sigma, a subset of complex plane, we consider the optimization problem over L as follows. So we minimize kappa diag A minus LC, the spectral condition number of A minus LC over the gain L, such that A minus LC has all eigenvalues in the set sigma. If we solve this one, then we find a gain L, and we actually find some Limburger observer system whose eigenvalues are in sigma, the set sigma. We say that the minimal value Q star will be equal to Q of AC sigma, and let L star to be a minimizing gain. And we are mostly interested in sigma to be the union of a 0 to a minus rho and one singleton 1 and complex disk of radius 1 minus gamma. And the resulting Limburger program, the resulting Limburger system provides the best observable linear representation of this true system among all possible linear predictors. Um, Now let's go get to fact two, sublinear regret. And for simplicity, I'll just put the result for a scalar case. And this will be our uh, prediction obtained from uh, observation spectral filtering with regression. And if we run the algorithm with P1 to T, and P1T equals 1, and all other P's to be 0 and all N's to be 0, uh, and if we choose the number of filters to be proportional to the square of log T, and the number of autoregressive components to be proportional to 1 of gamma times log of T over gamma, then we obtain that the regret relative to the Leuenberger observer system is sublinear, especially the square root of T, square root of T. And moreover, since the Leuenberg observer system is close enough, we can also say that the y hat itself is close to the true y t's, and the loss is bounded by square root of t, square root of t, which is sublinear. And we can. I want to note that because this big O tilde term has a lot of components, I want to note that there's the upper bound does not depend on a hidden dimension at all. And since we didn't assume any any noise process, this algorithm is proposed to like noise, especially like adversarial noise. Now we can talk about experimental result for linear case briefly. The left case is a case for random linear dynamical system with a correlated noise process, and the right case is for a linear dynamical system with permutation matrix, a transition matrix. And for the left case, when we have like a spectral filtering case, the correlated noise process does not stops a learning process. But if we add like the observation part of spectral filtering, then we can see that the loss is reduced much faster. For a permutation case, we assume that A is some 16 by 16 cyclical permutation matrix with noiseless case. And this permutation matrix is hard to learn because its eigenvalue are all 1, and it is marginally stable case. So it is much harder to learn. And for spectral filtering case, the loss is almost like stopped at this like 1.25. But if we add observation spectral filtering, then we can see that loss is decreased exponentially faster than the spectral filtering case. Now we consider nonlinear systems. It approximates, so the fact 1.2 says that it approximates nonlinear systems arbitrarily well over a long horizon. We consider xt plus 1 equals f of xt and yt equals h of xt. And we recall that all states and outputs are bounded by R. And we consider S an epsilon net of the ball of radius R in X, a state space, and let N be the cardinality of the epsilon net. And by the construction of epsilon net for all X in the possible like state space x intersection of x and the ball of radius r, there exists s in the epsilon net such that x minus s is less than epsilon. And we can enumerate the elements of S as S1 to S superscript n. We define pi a projection, which is the nearest neighbor projection, which means that pi of x is some argmin of s, argmin of x, the norm of x minus s over all s. And we also define t from s to s as t of s equals pi of f of s. And it yields a deterministic Markov chain with states S of t. And let Z sub t to be the one hot vectors indicating the states. And if we define A prime to be an n by n matrix with A prime ij is equal to 1 if t of s superscript j is equal to s superscript I and 0 else, then and then you can say that z sub t plus 1 is equal to A prime zt. And if we define C prime to be whose columns are h of si, then y prime t will be equal to c prime times c of t. Then we obtained a linear system. And we want to say that this linear system approximates the nonlinear system arbitrarily well over a long horizon. So assume that x naught to xt be is a trajectory of true dynamics with observations y naught to yt. And let S0 to be pi of x0 and st plus 1 equals t of st with a Markov chain. And define psi t, which is the difference between st minus xt, the distance between st and xt. Then psi t plus 1 by definition is equal to st plus 1 minus xt plus 1. And st plus 1 is equal to pi of st plus 1, which is the definition of t. And xt plus 1 will be the x of f of xt. And if we put f of st on the both, if we subtract them, add f of st and use triangle inequality, we will have two terms. And the first term will be bounded by st minus xt because f is one Lipschitz, and f of st minus pi, f of st will be bounded by epsilon. And since this is bounded by st minus xt, it will be x psi t. And by definition, psi naught is bounded by epsilon. We will have by recursively, we can say that psi t is bounded by t less than t times epsilon. And one Lipschitzness of H says that y prime t minus yt is less than t times epsilon. So if we add them all for over all trajectory length, t equals 1 to t, and this summation is bounded by horizon t squared over 2 times epsilon. And for example, if we choose epsilon to be t to the power of negative 3 over 2, then this term will be square root of t, right? Then on the average of this loss will goes to 0 over a long horizon. Then now we are left with a high dimensional linear dynamical system, right? A system that approximates the original system. So we apply the linear case again, and we obtain a sublinear regret as well. will be an experimental result using Lorentz system. A Lorentz system is a is defined as follows, and this is some example. So if Lorentz system is quite unpredictable, which so this that there are this these are two paths with very close initial points, but giving different very different path. And this will be the result. So for example, and they compared four different methods: LDS, EDMD, SF, SF, EDMD. So LDS will be at this form, where they predict the future observation by just using in linear dynamical system problem. For and for SF, they also use linear system, but they use spectral filtering case. And EDMD is an extended dynamical mode decomposition method, and SFEDMD is another EDMD method combined with spectral filtering. As we expected, LDS has the largest loss. And if you combine a spectral filtering, it gives better loss. But extended DMD has a better performance than just spectral filtering case. But if we combine spectral filtering to EDMD, you can see that it has much lower cost. And this is the left side is a fully observable case where XT is equal to YT is equal to XT. And on the right side, it is a partially observed case where we just use some random matrix C to find. So we apply some random matrix C to obtain just one-dimensional partial observation. And in this case, we can also see that spectral filtering in case are better than non-spectral filtering problems. And this figure shows the predicted path. The blue one is the ground truth path, and orange is EDMD, and green is EDMD combined with spectral filtering. And we can see that the green and blue are close together, and the orange one is the most like separated from the ground truth path. And the right one also it's from the right figure, you can see that non-spectral filtering case or EDMD has much worse prediction than SFEDMD. To recap, we learned about observation spectral filtering, and we showed that this provides a universal, provably efficient approach to learning nonlinear dynamics by competing with the best possible linear observer, which we called the Limburger Observer Framework. Thank you.